Get started. So today, what we're doing is we're continuing our journey with the kinematics of rigid bodies, which is basically my favorite topic in dynamics. And today, what we're going to look at is general. You guys can see my screen and hear me all right, right? So we're looking at general plane motion, and all that general plane motion is you're combining rotation with translation as well, right? So it for a rigid body, general plane motion, when you're moving in one plane in a two-dimensional manner, it's describing any motion that you can possibly have because you're combining rotation and translation. And because it's a rigid body, the body cannot elongate or deform, right? That this general plane motion can be used to describe the motion completely, right? So what is general plane motion? So the easiest way to get into general plane motion is to consider rolling, right, of a disk. And we're going to take a look at rolling more carefully, but this is just to consider this whetting your appetite. So we have, let's say that there is a disk, right? And the center of the disk is at point A1. And let's just say that a point directly on top of the center, right at the highest point on the disk, is at B1, right? And this body is undergoing rolling, right? I mean, it need not be rolling, it would just be sliding plus rotation, but for all intents and purposes, for this example, let's just say it's rolling and it moves along. What's going to happen is it moves into, let's say, a new position whereby the center has translated, right? Because the center is not going to rotate in this case, and it's moved, A has moved from position 1 to position 2, so it's at point A2. And then due to the rotation of the body, B1 would have rotated and moved to another point. So let's just say that this point is called B2. So this combination of translation and rotation is what we call general plane motion, right? So this is plane motion. And the way to describe this motion is by breaking it up and superposing translation and rotation on top of each other, right? So what you can do is you can literally break it up into, let's see. So now let's see what happens when you have pure translation, right? So in pure translation, it's there. I've got my, oops. Got the ball like that, right? So in this case, where you're just looking at the pure translation, or all points move with the same displacement, right? So I can say that A1 has moved to A2, so the centers remain like that. And we can also say that, let's say that B1 moves to this position, B1 prime, right? And this is the translation aspect, right? And then you can look at the rotation, which basically moves B1 prime to B2, right? So you have right? So due to the rotation of this guy, you'll see that B1 prime moves to its original position, B2. So what we've done here is we've basically broken up this motion, this plane motion, into translation and rotation. So that's the concept of how you want to think of general plane motion, right? So if you write that out, we see that general plane motion is not just translation, nor is it just a rotation, right? What it is a sum of the two, what you can think about, a combination of the two, right? So it is basically but a sum of a translation and rotation. And guys, going forward, I do things like, I think I told you this, I do things my own way in rigid body dynamics. The book is good. It's a very good alternative, but we're in chapter 15 if you care to look at it. But I do things which slightly more in a more succinct manner. So now if we look at general plane motion, so this was very specific for something that was rolling, right? Now let's generalize it so that we can derive our equations of motion, right? So now let's look at a body. So you have some body like that, then that translates over into this new position 2, and then it also rotates about some point. So let's say that it ends up rotating. So it's basically gone from this configuration into this hard configuration over here, which is a combination of the translation plus the rotation, right? So let's figure our points out. So in position 1, we have point A. Position 1, we have point B, right? And breaking up the motion, we've seen that A1 is going to move to, let's say, to this point A2, right? And B1 is going to have the same translation onto, let's say, it moves to, as keeping the configuration the same, say B1 prime, and then it rotates about this point to move into its final position, which is B2, like that. So this is a rotation, right? So what we've seen in this rigid body motion is the displacement of all particles in the rigid body, right? So we have A1 and B1 to A2 and B2, right? So we have translation to A2 and B1 prime, and then we have rotation of B1 prime about this point, A2 to B2, right? So this is general plane motion for a general body, right? Then we can actually start looking at the velocities and the accelerations, right? So let's get into that. So we have the absolute and relative velocity in this plane motion. Right, so let's do our derivation. So let's say that we have some body. Every time I say somebody, that song, now you're just somebody I used to know keeps starts playing in my head. I don't know how old you guys are, but that was like way back in the day. Yeah. So this has basically translated and rotated, right? So let's see, and let's do it over a short period of time. So we are at a time period of, let's say, t over here, and then this has moved such that it's over a very an infinitesimally small period in time, right? And what's happened is that A1 has moved to position A2, right? So we can define, well, we'll define the vectors afterwards. And then we can say that a point B1 has moved to a point B2. Relative to each other, they remain the same, all right? This distance between, because it's a rigid body, right? So in a rigid body, points don't move relative to each other. So relative to each other, the distance remains the same. So what I mean by that is, if I define a unit vector of B relative to A, and in this second position, I define one again from B relative to A, which is, let's call it prime. So R prime B relative to A, the magnitude of R of B relative to A and R of B prime, R of R prime B relative to A, the magnitude of these vectors is going to be the same. That's just the definition of a rigid body, right? The distance between points on a rigid body don't change. All right, is that clear to everyone? Okay, and then let's define that this point A has moved by a really small vector dra, and the point B has moved really small vector drb like that, right? So we're moving from position 1 to position 2, and what we've done here is that the object moves from position 1 to position 2. And what's happened is that it has both translated, right, and rotated, right? And we're only looking at this in 2 dimensions, right? And in our class, we're only going to be focusing on 2 dimensions. 3-dimensional stuff you'll get into when you start working with machines and mechanisms with Dr. Garashi, right? So this is always the problem that we're doing is it's in the plane of the taper, right? And that's why it's called plane motion, because it's always happening on one plane, right? So let's do what we've been doing to derive our expressions and break this up into translation and rotation. All right, I'm moving on to the next page. All good, guys? Okay. So when we look at translation, right, so you'll have that. So you have point A1, point A2, then you have B1, and then you have B1 prime, right? Just using the same convention we've been using so far. So B1 prime, right? Again, you have this vector here. So this is going to be R of B relative to A, and this vector remains the same in pure translation, right? In pure translation, the magnitude and the direction remain the same, all right? So A has moved by dr A, right? And B has moved by drb. What's the relation between dra and drb? In this for pure translation? What's the connection? They're the same, right? This is a whole body and all the particles have moved and translated the same amount. So this is just the same thing as dra, right? You guys with me? And then we combine rotation into this, right? And this rotation, we're saying that it's happening about the point A2, right? So let's see. So this is this original configuration, and then it rotates and it becomes, say, something like that, right? And the rotation we're saying is happening about the point A2, right? So you have B1 prime there. So, whoops. So you have R of B relative to A, which rotates onto B2, right? This has become what we had said, R of B relative to A prime, like that, right? And the movement from B1 prime to B2, let's say this vector here is described by D of R, the change in the position of B relative to A. All right, is that clear? So now for this plane motion, we can write that for this point B, drB is just equal to this translation, which is dRA, plus this rotation which has taken place, which is just dr of B relative to A. And that's it. What your book spends 5 pages doing, we've done in half a page, right? You differentiate this expression and you get your expression for the velocity in general plane motion. So we differentiate with respect to time, and what you get is this expression. You see that the velocity of any point, rigid body, is equal to velocity of any other point on the rigid body plus the rotational component, right? So this part here is your translation, and this part here is your rotation. Now, the magic of this, all right, before I tell you guys what the magic is, for this rotation part, we know this is what we looked at last week, which seems like ages ago. For pure rotation, we know that velocity of B relative to A is just equal to whatever is the angular velocity of your rotating body, right? So for this rotation, you can describe an angular velocity and you can describe an angular acceleration for this rotation, right? So that ends up being omega crossed with R of B relative to A. And now here is where the magic comes in. This expression that you see over here is true for any 2 points on a rigid body. Undergoing general plane motion. So as long as you pick any 2 points on your rigid body, this expression is going to hold true. Why does this intuitively make sense? Because this rotation that you describe for this body is independent of any point on the body, right? The rotation is just coming out of the plane of the paper and it's going to be in the k-hat direction, right? You don't need a point or an axis location to describe the rotation of this body. Therefore, this expression here is valid for any 2 points on a rigid body that is undergoing general plane motion. If that doesn't make sense, we're going to look at instantaneous center of rotation in the later half of today's lecture, and then it will make sense. All right. So in general, you can write the expression for a rigid body undergoing plane motion again, as I said, for any 2 points, can say that the velocity of the point is equal to velocity, that's the translation, plus the rotation aspect of it. So R of B relative to A, like that. But that's the trick though. When you're looking at, and this is where the slight intuition confusion might come into the picture. You always have to look at 2 points when you're looking at general plane motion. You can't just look at 1 point. Does that intuitively make sense to you? Because if you just look at 1 point, you can't describe both translation and rotation. In order to describe translation and rotation on a rigid body, you always have to look at 2 points. All right?
Yeah, that makes sense because it's always going to be relative, right?
Exactly. Absolutely. And the reason, as we said, that it applies to any 2 points is the fact that the angular velocity omega of a rigid body in plane motion is independent of any reference point. Now, we're going to take a slightly harder look at this next week when we look at frames of reference, centroidal frames of reference and things like that. But hopefully intuitively right now, this makes sense to you guys. All right, and that's it. We're done. Now we're just going to differentiate this to find out what the accelerations are going to be. All right, good to move to the next page. Am I not good to move to the next page?
No, we're good.
All right, awesome. So now let's find out what we call the accelerations in general plane motion, but people like to refer to them as absolute and relative accelerations. And right now, this differentiation does not make sense, but next week it's going to make a whole lot of sense. We're basically just setting things up right now. So for general plane motion, right, we had said that for any 2 points, instantaneous over a really, really short period of time, the expression to describe the change in position was this expression, right? So drB is equal to dRA plus dR of B relative to A. All right, and easy peasy. All you got to do is differentiate twice with respect to time. Right, and the expression that you end up with is simply the acceleration of point B is equal to the acceleration of point A plus the acceleration of point B relative to A. And the exact same interpretation that we had for the velocities, right? So this is translation, and this is rotation. And again, as we said for the velocities, pick any 2 points and you're good, all right? They're independent of the 2 points. Now we know from last week, hopefully you guys remember this, for pure rotation, that when you have acceleration of B relative to A, that has an angular acceleration component, right? So alpha crossed with R of B relative to A. And then it also has this other acceleration component, which is the triple product, right? So that's omega crossed with omega crossed with R of B relative to A. So the centripetal acceleration component. All right. So plugging and chugging, we get for a rigid body undergoing general plane motion, right? Again, for any 2 points, get the expression that the acceleration of point B is equal to the absolute acceleration of point A plus the 2 terms that come due to the relative acceleration, which is the rotation. So that is alpha, which is the angular acceleration, crossed with r of B relative to A plus omega crossed with omega crossed with r of B relative to A. And this is your all-important expression. And with that, you guys have all the tools that you need for homework 7, which will be assigned on Tuesday. All right. For all of you who might have seen similar stuff in physics, right? Or if you want to simplify this, and this is what I don't like about the book, because I just like to keep things as vectors, put them into Mathematica, make sure my equations and unknowns are equal, and just solve it, call it a day, right? The book likes to think that it's making the math easier, but for me, it's not easier. You guys might think that, right? In that case, what you can do is, for this plane motion, you can look at this simply to say that for motion along the plane that is perpendicular to the axis of rotation. So basically what we're doing right now, perpendicular to axis of rotation, right? You can straight away write that the scalar component of V of B relative to A is just going to equal R times omega, as long as you can define that, you know, R is distance from A to B, and you can write the acceleration of B relative to A. Now this one, I don't recommend doing directly, right? So always just find out what your vector cross product is. You know, you guys know what k hat is, right? It's the direction coming out of the plane of the paper minus, and the triple product you can write as omega squared times R of B relative to A, like that. I don't recommend you do this, but if I'm only going to do vector algebra going forward, if vector algebra for you guys doesn't make sense and this makes more sense, feel free to use it. All right. So this is your tangential component, which is R alpha. And this is the normal component of the acceleration, which is R omega squared. My recommendation would be just use vector algebra, make sure your unknowns and equations equal each other, and solve everything in Mathematica. That's how I do it. Keep things simple. Just set up the problem and forget about everything else. But if that doesn't make sense to you, you can go ahead and use these expressions like physicists like to. So, yeah.
Which one do you recommend again?
Just directly using these expressions, vector algebra. So you will see basically how we do the problems going forward. You're going to see it.
Oh, okay, thanks.
Yeah. My recommendation is to just directly use these expressions for acceleration and for velocity, and then tailor those to whatever your problem is. All right. And the last thing we want to cover today is another sense where you can think of the fact that, all right, I can pick any 2 points on my rigid body and I'm good to go, right? Is this concept, which is called I'm not going to test you on this on the exam, but you will have a homework problem on it, all right? So this is called the instantaneous. And again, for the homework problem, you need not use this method to do it. You can use there's multiple ways to skin a sheep or a goat. What's the saying? Something like that, right? Center of rotation. So what this means is that for any body in general plane motion, you can describe it as pure rotation at any particular instant. At any particular instant, it can be described as pure rotation. And that's why at any particular instant, if you just pick 2 points, you're good to go. All right, so let's get into it. So we say that, oh, by the way, did I change pages too quickly? Are you guys good with this? All right. All right, so for plane motion in which the axis of rotation is perpendicular. So this is just the definition of general plane motion that we keep writing again, right? So these theories are only valid for general plane motion. So perpendicular to plane of motion, right? Rotation about any point is independent of the choice of reference point. All right, you can tell me, Ashish, so many words, you're confusing me. Don't get confused. All that we're trying to say over here is that as long as you pick any 2 points on a rigid body, you're good to go, right? And why this makes sense is that because at any particular instant, right, remember, these expressions are only valid at a particular instant, right? So you have to look at the particular instant that you're doing. If you're changing instances, then what do you guys have to do? If you remember from kinetics of rigid bodies, if the time changes, what's coming into the picture? You have to start thinking about impulse, conservation of energy, momentum, and things like that. All right. So right now we're only looking at stuff that's happening at a particular instant. All right. So at any instant, motion of our random point that we've been calling B about any point, right? About any other random point C, we've just done this derivation, is described by velocity of B is equal to the velocity of the point C plus omega crossed with R of B relative to C. Now, at any particular instant, what you can do, because you're engineers and you have this power, is you can define a point about which the velocity of that point is going to be 0. And that is known as your instantaneous center of rotation, right? So at this instant, and this is exactly the amazing, yet what I'd like to think unnecessarily stupid things engineers like to do, which they think that they're making their lives easy, but not really. You can say that the translation is equal to 0, right? And therefore, what happens to this expression on top is that velocity of point B is just going to equal omega of R of B crossed with C. Therefore, for any other points on your body, right? Let's say A and D, you have the same expression with just a slight change in your, the only thing that's changing is the position vector, right? So omega of R of D crossed with C.
Is this if translation doesn't exist?
Nope. This is for, there is at any particular instant, there is always going to, you can always find a second point C which doesn't translate. And give me a second. Intuitively, mathematically, mathematically, hopefully it makes sense, right? You found this point about which the velocity is equal to 0, right? And about that reference point, these are the expressions that you get for any other points that are there on your body. And it's known as the instantaneous center of rotation. Now, you can be like, sheesh, I don't understand what you're talking about. Please make my life easy. So if you look at any body, right? And you're looking at, let's say, point B, you're looking at point A, and you're looking at point D, right? The velocity in this particular instant for B is like that, for A is like that, and then for D, let's say, is like that. What you can do is, for this particular instant, if you draw the perpendicular to the velocity to the point, right? So if you draw this perpendicular, this perpendicular, and that perpendicular, they will all intersect at the same point. And that is your magic point C, which is the instantaneous center of rotation. And you can say that this plane motion at this particular instant can be described as a pure rotation about this point C. Mr. Rushford, does that answer your question?
Yes, thanks.
And point C is called as the instantaneous, comfort dynamics, learn English, instantaneous center of rotation. So basically, what we've done is we've described for general plane motion, a couple of things are important. When you're looking at rigid body motion, right? And you can straight off just seemingly assume that it's going to be in plane motion, right? Because plane motion is rotation plus translation. If it's in pure rotation, then the translation aspect of it is equal to 0, right? But now throwing some water onto those theories, you can find out a particular point at all instances about which you can describe the general plane motion as pure rotation, right? But in general, what you want to do is, when you're looking at rigid body motion, you always want to look at 2 points. It doesn't matter how those points are referenced to each other, but you will get the hints from your problem which points to look at, all right? But in general, as long as you just look at 2 points, you'll be able to describe their motion pretty well, all right? And these expressions, so this expression here, right? VB is equal to VA plus omega crossed with R of B relative to A. This is super important. And then this expression here for the accelerations is super important, right? So acceleration of point B is equal to the acceleration of point A plus the angular acceleration component plus the centrifugal, whatever, physics acceleration component over here, right? Let's go with tangential and normal. That's better. Okay. Awesome. With that, do you guys have any questions?
So for the two vectors, is there any way to mathematically think that they're like parallel in any way, or are they gonna always just have different directions?
Which vectors?
Within the body.
You shouldn't have 2 vectors within the body. You should only have 1 vector within the body, which is the position of one point relative to the other.
Oh, maybe I was just thinking of the position.
Yeah, so for the position, right? So if you have your body like that, and you've got that's your you're all right. Let's say that this is your body and you're selecting point B and point A like that, right? For all intents and purposes, if you're concerned with the motion of point B, right? In that case, you will always have to find R of B relative to your reference, the second point on your body, right? And
Yeah.
this you can just find as from some fixed reference, it's just going to be R of B minus R of A, right? This is just from the vector algebra, right? Remember,
Yeah.
the absolute position is equal to the relative position plus the absolute position of the reference point, right? I don't know if that answered your question.
No, it practically did.
Okay. Awesome. All right, so let me save this. Good stuff. All right. I'll post the problem set on Tuesday if that's all right with you guys. So let's just look at, because we're only going to do one problem today because that's all we have time for. Or do you want me, you know what, I'll just post the problem set. But the problem set I'm posting today has problems from both today and the problems that we're going to do on Tuesday. All right. Okay. So did I get lost? Oh, there we go. Right. It's like when we do algebra, when we do these discrete mathematics, digital logic, when we do statics, maybe you get strength of materials, you really see like, all right, now this, what we're learning really makes sense in designs of structures and things like that. Here's another example, right? While we're learning all these things in dynamics, Ashish, because you can start looking at motions that engineers need to do, right? So here you've got a very, very famous mechanism whereby you're converting rotational motion into translational motion. It's a piston, right? Basically how cars work, right? Actually, it's the other way around. You're converting translation motion into rotational motion, right? This is basically how pistons work. All right, so in this question, you're told that the length of link DB is L, and you're told that that's equal to 160